for the introduction. Good. Yeah. Yes. Then we have this conference title called the structure integrated. But now we will see if it's possible that we use our knowledge from the fractal mechanics to actually break the structure integrated of the certain system. And that's how we can use it to remove ice stuck on the surface. So this work is done by our PhD student, former PhD student, Dr. Feng Wang, and with my colleague, Professor Senbo Xiao and Professor Zhiliang Zhang. And probably some of you know that in Norway, we have really this icing problem from the cold region. We would say that the winter is starting from October and until sometimes even June next year. So in this long winter, we have a lot of problems of icing, and especially in some key sites. For example, the emergency exit of the buildings, of the oil platform, the wind turbine, the power cable, all those areas, we want to keep them ice-free. Unfortunately, in the continuous low temperature and long winter, and often we have the icing problem. So how we can rebuttal with the ice to avoid ice formation, to remove those formed ice on the surface is a big topic. So my outline is that first is using the fractal mechanics knowledge to enable those isotopic surfaces. And then come to the topic today that phase scale enabled low ice adhesion. Some other biomimetic isotopic surfaces than the phase scale, and come to the summary and the perspectives. It's easier to understand that when you have the ice formed on the surface, then we use some active de-icing method. That means we pump energy to remove ice. And it could be mechanical, the thermal, or the chemical method. Problem is that all those active methods we are using, we need to pump a lot of energy, and it poses the environmental hardness. And sometimes also it's difficult for the current technology to reach those areas like the power cable above, or like the wind turbine blade. Then we probably need to combine those active methods with the passive and the icing surface. What does it mean is that the surface itself either could repel the coming water. If we never have the water form on the surface, then we don't have the resource to form ice. That's like the super hydrophobic surface. Or if we have a surface, we accept the water coming, and it can delay the freezing time. Then we have time to remove those water droplets. But the problem is that in long winter, continuous low temperature, that super hydrophobic surface, all this delaying drop freezing time are not realistic. It could work maybe for like the several hours, but not this long winter. So the realistic strategy is that we live with ice, but with the lowest ice adhesion. So by the gravity force of the ice itself, or any small vibration like the natural wind, then the ice could fall automatically from the surface. So that's with the lowest ice adhesion. Then question come out that how we could lower the ice adhesion. And from the fracture mechanics point of view, that if we have an ice cube and stay on the surface, then its shear stress is proportional to the square root of the Young's modulus of the index, the surface energy, how the ice interacts with the subsurface, and also the crack length. So here you can see that what we need is to reduce Young's modulus, reduce the surface energy, but increase the crack length. And that's very opposite to our structure integrated concept. And previously that people work on different strategy with lowering the Young's modulus, lowering the surface energy. For example, design the surface with the lubrication layer, and that of course reduce the surface energy, or make a very soft surface to reduce the Young's modulus. What we have been focusing on previously is to design the multi-scale crack initiator promoted surface, where we design those subsurface structure. We don't work at this interface, but design this subsurface structure to maximize the stiffness in homogeneity between the ice and the subsurface. So we can keep certain robustness of the surface, but still maximize the crack length at the interface. And this has been proven quite successful, and we got a lot of attention for our massive strategy for lowering the ice adhesion. So then, of course, that we are not satisfied with that. We should continue to find the new possibility to lower the ice adhesion. And one of that is that this anisotropic ice adhesion on the fish scale. Yes, in Norway, we have the advantage, a lot of salmon around, and it's huge salmon. So it's possible to get the enough sample from even just one salmon. And the salmon we bought is around maybe 10 kilograms. And then we carefully peel all the skin out. And the concept is that, think about this fish scale, they grow directional. And if we remove ice along the 0 degree, along the growth of the fish scale, or 90 degree, then probably we don't see any like the difference from the interface fracture. We have such concurrent rupture at the interface. But if we peel this ice cube against the growth direction of the fish scale, then we can realize that this opening of the fish scale one by one, and realize this sequential rupture. And this sequential rupture, of course, you can see here that then we reduce the contact area between the ice and the fish scale, and in a way to minimize the ice adhesion. And this is the conceptual design. So let's see how this result looks like. Video shows how this opening process of the fish scale. We use a PVC tube to grow the ice on the surface in series, and then push this ice cube. Then you can see the opening of the fish scale and expanding of that. Also, initially, actually the opening is one by one. And you will see the result, how it looks like, that as the adhesion spread, we compare this sharing along different angle of the fish scale growth. And it's obvious that we do it at 180 against the growth direction. It has the lowest ice adhesion. And interestingly, there is also side effect. Although it's the fish scale from one big salmon, but it has this scale size from different parts, different scale size. What we can see is that actually this scale size also includes this ice adhesion. And interestingly, that the experimental results match very well with the molecular dynamic simulation. In the molecular dynamic simulation, we use this graphene platelet to represent each individual fish scale. And we do in different directions of the shear test. And found out that also this 180 gives the lowest ice adhesion, and it also connected with the size of the plate. If we compare our fish scale test with the other artificial materials, like the technical copper, steel, aluminum, those the metallic material, or ceramic, or other the polymer composite materials, and we can find that the fish scale has reasonably high Young's modulus, but very low ice adhesion, attributed to this the sequential rupture of the fish scale. This unique fracture mode lower the ice adhesion. And just a very small part about this fish scale enable the isotropic ice adhesion. Of course, we also work on other type of the biomimetic materials. For example, that this ionic gel surface mimic how the ion migration through the human skin. And this ion could diffuse from the substrate to the interface, melt the ice at the interface, and lower the ice adhesion. Also, like it's the similar to those like the frog skin, it has this porous structure containing lubricant. It can simultaneously diffuse into the interface and create a lubrication layer at the interface and lower the ice adhesion. All like this, not only about the nature creator, also like this plant enabled, like onion-like surface. The onion surface has very complex surface structure with the pore, something here, with those pocket structure. So we mimic those onion surface and also achieve the very low ice adhesion. It's all below 10 kilopascal, very low. And of course, that combining all different functions of the coating we need, for example, the self-healing property, the transparent coating. Thinking about this outdoor web camera, where we need always the transparent coating to avoid ice formation. And also, if any those mechanical cutting damage to the surface, the self-healing will help to cure it. And then we can see this multifunctional coatings also has a reasonably low ice adhesion compared to those the original, the intact surface. Yeah. A very short presentation, but just bring this message to you that how this the fracture mechanics concept could help to lower the interface adhesion, and especially that this phase scale enable this sequential rupture mode to reduce the ice adhesion. So our next step is that if we have other type of those phase scale, all new fracture mechanics enable the fracture mode to lower the ice adhesion. And if we could use the 3D printing method to mimic those the bio surfaces for low ice adhesion. And if you have any idea about those like the other type of the surface, we are very eager to collaborate. Yeah, with the funding agency and a winter picture of our headquarters at the university. Thank you for your attention.